for explaining, okay? As I told you, M&MoCS has a short story. It has been founded something more than 10 years ago, but we try to behave in the French way. So we try to make what French people call pérennisation. We try to make it permanent. Okay. So first thing, we need young people, and this is the reason for which I'm inviting so many young people. But also we need to give credit to people who work for science. You know, we are in general, except few lucky exceptions, scientists are not rich. And we are simply rich of glory. So I think that if somebody dedicated his life for the advancement of science, which is useful for the next generations, try to explain to our politicians that what we are doing now will not be useful tomorrow, but it will be useful in 50, 100 years. So I think that it is worth to recognize the contribution to science of some people. Together with the successors of Levi-Civita, many years ago we decided to establish the Levi-Civita Prize. It is, I believe it was a scandal that nobody had conceived this before. Because Levi-Civita was not only a big scientist, huge scientific contribution in many fields. There is also a paper about the stability of a blackboard. Because he was falling on the blackboard and you know, he wrote the Lyapunov equations of it. Okay, he was a multifaceted man, not only a mathematician expert in tensor calculus. Okay, but you know, he was a victim of Russian laws. And in this moment of European history, maybe it is worth telling that the best pupil of Levi-Civita, Antonio Signorini, who had got a chair in Palermo being 27 years old because of the help of Levi-Civita, wrote a letter to Mussolini telling that Italian science does not need Levi-Civita. We can get rid of him. Okay. I think that we must remember these things. Okay, this is for giving you the framework. Then, you know, I feel embarrassed, but I will tell something about Sébastien Candel. Embarrassed because I am ashamed to be never comparable with his achievements. You know, he has, I can tell you something. He has been president of the French Academy of Science, together with Lagrange, Laplace, Arago, Poincaré. These things are frightening. Okay, but in the spirit of the M&MoCS Center, he tried to attack with the typical French viewpoint. By the way, at the French Academy I said that Italian and French science are the same, and Italian and French are the same language, spoken in a different way, but let's talk about science. Okay? In the typical way of every French scientist, he attacks complex problems with mathematical rigor. You know, French people are like that. They were trained for doing this. So his research was reducing models from complexity for trying to get predictive, some predictions which works in applications. And I had already seen something, but yesterday night I had a crisis of anxiety, so I went to read one of his review papers, and it is impressive what he has done, his group has done. I will simply conclude telling that the big difference between France and Italy is that he was allowed to work without fighting against jealousies, which instead are typical of Italy. The French system allows you to work. So he could design the engines of Ariane and study Ariane stability. I decided not to tell you many details because I don't want to risk to say something which is not precise. And Sébastien is a precise one, so he could be upset if I don't say exactly the words. What is astonishing is that French science, represented here very well, is able to be at the frontier of theory, but they can do practical things. There is nothing like practice without theory. Okay? So I will now invite him to give his talk. You know, you allow me to make a joke. In Rome, we gave the medal at the end of the first edition. We gave the medal at the end of the talk, and the resident told me, you examined me before giving me the medal. So we started giving the medal at the beginning, but at Sébastien's request, we will give the medal at the end. Okay? So please, Sébastien.
Thank you very much. Do you hear me in the back? Is it okay? Let me just say something about what you just said. You know, Karman or Einstein was saying there is nothing more practical than a good theory. So keep that in mind. Theory is very important. All right. So it is a pleasure to be here. It's a pleasure to tell you about the complexities on which we work. I spent my life now on these difficulties, and I'll tell you how we have advanced the system. I thought I should say something in Italian as well, not just English. So, un sentito ringraziamento al professor Francesco Dell'Isola, direttore di M&MoCS, per avermi invitato a tenere questa conferenza. I understand everything. È stato un piacere preparare questo discorso e sono felice di condividerne i contenuti con voi.
The same language pronounced
in a different way. Yeah. And so my aim is to discuss the complexities of combustion. This meeting is about complexity, examine key issues, ways of how to deal with them, describe recent investigations in combustion dynamics, applications to aviation, gas turbines, and liquid rockets. It's bold to try to examine all these topics in a limited amount of time. This will be an overview, and in French we say un survol. You fly over, and in Italian una panoramica. So it won't be too deep, it will be more to give you a flavor. I met Francesco at the Academy of Science. We invited him to give a lecture. The title was about mechanics in the French style, and he did it beautifully. And at one point he was explaining that French is like Italian. They are the same language, but pronounced in a different way. I'm not so sure. I don't understand the Italian so well. Francesco gave a superb lecture, and I advise you to listen to him, but it's in French. This is on the web, and you can take a look. Before coming here, I listened to him again, and I liked him very much. It was nice. And he was presented by our friend Yves Raymond. He suggested the invitation, and I was glad to do it. All right, let me tell you a little bit about our lab. Initially, the school where I'm from, École Centrale, was in Paris. You see Paris is in the middle there. And later on, the campus went to Châtenay-Malabry. You see the formal location is in blue here. And 50 years later, there was a decision made to move again. So we moved from one place to the other. So you have more and more difficulties because you have all the experiments to bring from one place to the other. This is the former location. You see, we had a very nice lab with a lot of people, and it was really a very good way to make a group and to work collectively. One of our alumni is very famous. This is Gustave Eiffel, you know, the man who built the Eiffel Tower. Eiffel was a very big engineer, and in fact he died in 1923, and so it's 100 years after his death, and there is actually an exposition at Centrale. The school itself has merged with Supélec. Supélec is another school in electrical engineering, so we have mechanical, electrical engineering, and industrial engineering in general. And yeah, still another pioneer in aviation is this pilot, the test pilot, Constantin Rozanov. This person was able to travel against the sound barrier in 1954, just a few years after Charlie Yeager in the United States. In 1954, Charlie Yeager was in 1947. This is Eiffel. At the end of his life, he was interested in aerodynamics, and he built wind tunnel, open wind tunnel, which are called Eiffel wind tunnels. You see, you have a nozzle on one side, and there is a diffuser on the other side, and you can put directly the wing or the model scale of your airplane inside this wind tunnel. And he did a lot of very nice studies about aerodynamics. The drag of spheres, for example, was treated by Eiffel, but he treated also the drag of airplanes. And for that, he was given the second Langley Medal by the Americans. So they recognized his work. He was not only an engineer, but he was also a scientist. And this was done after the age of 70. So he was very active during his retirement. He worked. Another famous engineer from our school is Blériot. Blériot was the first to cross the English Channel, La Manche, to go from France to England by airplane. It took him half an hour. So he had to find a good engine because otherwise he would fall in the water. And he succeeded. He had many failures, but he succeeded. He was a very good engineer as well. And why did he succeed? It's because the engines in France at the time were twice as effective as all the other engines in the world. France was in advance. The power density in the engine was twice that you could find in other countries. And so he was the first to cross the channel by plane. He was not the first to fly. Of course, the Wright brothers are really those who flew first. And in fact, the Wright brothers came to France, demonstrated their aircraft. There was a lot of enthusiasm in France for aeronautics. Everybody wanted to fly. And so there was a very strong connection between the France and the United States. Not so much in terms of drugs, what is shown in this film, the French connection, but in terms of aviation. All right, let me now come to complexity. Of course, you have this very nice crowd. We have somebody called Sampé in France, and he did beautiful drawings of that kind. Every little person in this is interesting to watch. And of course, this is quite complex. Look at all the interactions that are taking place between everybody with the cars and everything, and trucks. But of course, combustion is not of this kind of complexity. The complexity in combustion comes because you need many sciences. In fact, at least four. The four of them are chemical kinetics. It's a matter of reaction, so you need chemical kinetics. You need fluid mechanics, because everything is in fluids. There is a little bit of solid as well, but essentially combustion is in a fluid. You need the thermodynamics of mixtures, because it's not a simple fluid. You have to take into account the fluid, and sometimes it becomes quite difficult. It's not an ideal gas. For example, in rockets, you have a situation where you are above the critical temperature and above the critical pressure. So this is unusual. And then also we need multi-species transport, and this is again quite a difficult thing to represent all the fluxes of the species one into the other, to represent also the heat transfer. You have also radiation, so you have all this, and it's a combination of all that. And then you have to look at many problems, the many modes of combustion. You have a variety of possibilities. The configurations are different. The geometries can be complex. You have operational conditions which are quite varied. You have this complex kinetics problem. The reaction rates are stiff. That is, they follow Arrhenius' law, and you know that Arrhenius' law is exponential with respect to temperature, and so this is a stiff problem. Immediately you get difficulties in terms of mathematics. You have thin layers. The flame can be very thin, typically of the order of less than a millimeter, and the combustor is large, so you have a multi-scale problem. And in addition, you have turbulence there, but I'll come to that. Critical conditions. Sometimes you ignite and sometimes you don't. And you have also extinction. Sometimes you blow the flame and it's out. So the solution is gone. You have multi-phase because many reactants are injected in liquid form, sometimes as a solid. In fire, for example, you have solids which are burning. You have strong interactions with acoustics. This is when there is a resonance, this can cause many problems, and this gives rise to combustion dynamics. I'll show that in a few minutes. You have high pressure and transcritical conditions, liquid oxygen injected at low temperature, and then at a pressure which is much higher than the critical pressure, and you are transcritical. Of course, you have the complexity of turbulent flows. This is really a tough problem to deal with turbulence. And everything is multi-physics with coupling, with radiative transfer, and so on. And in a practical application, again, combustion is difficult. You see, for example, in this engine, the combustor is very small compared to the remainder of the engine. But without the combustor, nothing happens, because this is where all the power is injected. So if your little combustor doesn't work, the engine is at rest. In addition, the combustor is between the compressor and the turbine, and as a consequence, the boundary conditions are not so easy. Even other interesting things to say about applications, especially high-performance devices, is that the power density is enormous. For example, in a rocket engine, you have a cubic meter of a rocket engine, and you have 50 gigawatts. That is 50 nuclear power plants in a single cubic meter. Now, the engine doesn't have a cubic meter. It's smaller, but typically an engine like the Vulcain expands something like about 2.5 gigawatts, 2.5 nuclear power plants. When the engine is operating, the power is so high. In aircraft engines, the power is pretty high as well. It's of the order of 1 gigawatt per cubic meter, and this is also the case in gas turbines. The pressures are extreme in rocket engines, 10 megapascals, 20 megapascals, 200 bars. Yeah. The modes of combustion can be varied, non-premixed for rocket engines, partially premixed in aero engines. You have complex flows. For example, the injection in an aircraft engine is swirling. Why? To anchor the flame inside the combustor. You don't want the flame to move out. You want it to be inside. The chamber geometry is, let's say, simple, cylindrical in one case, annular, because the axis of the engine has to be there. So you have an annular combustor in aero engines and gas turbines. It's interesting to look at the history. And I know you like the history of science. So knowledge of fire came to man 500,000 years ago, 500,000 years. So, and this is the beginning of civilization. Without that, This distinguishes us from animals. Animals don't know how to handle fire. We do. That's a big difference. And, but it took a lot of time to understand ignition. Ignition, it's about 30,000 years ago, 10,000 to 30,000 years ago. So a lot of time was spent without knowing how to ignite. You could use fire, but you could not ignite. Of course, fire is very useful. It's extremely useful to make tools, to eat, you know, your food, you know, And, but we had to wait for science to the work of Lavoisier. Lavoisier, in 1778, set the grounds of modern chemistry. Before that, the theory of combustion was in error, was completely wrong. You know, people thought that something would come out of the body, and this was the phlogiston theory, and of course, Lavoisier demonstrated that that was not right. The first theory of flame was developed by Maillard and Le Chatelier in 1870. And then we had very famous names like von Neumann and Jouguet and Zeldovich and von Karman and Frank Kamenetsky. These are really the founders of modern combustion theory. And then in the more recent times, you have a lot of developments. Theory has developed extensively. We use activation energy asymptotics, laser diagnostics and imaging techniques. We worked on complex chemistry flames. We are now able to handle very complex flames, and direct simulations and computation flame dynamics, and you'll see what we are doing now. Now, the state of the art at the times of Karman, I think all of you know Karman because he was also influential in solid mechanics. He did fluid mechanics, but he did also solid mechanics. He was a man of great breadth. And Karman and Penner were working on a very simple flame. You take ozone and you decompose ozone. That makes a flame, but it's a flame with two-step reactions. You have these two steps. So this was the state of the art in 1954. And it took them about 36 pages to write down the algebra to calculate the flame speed. The burning velocity of a simple flame was calculated by them. They were very happy with that. And they were saying, yes, we could foresee maybe to treat hydrocarbon flames in the same fashion. But it would have been extremely difficult to do it just by hand, just using the method. And in fact, we are able now to calculate flames with very complex chemistry. Even the chemistry, of course, you cannot write down all these equations, but even the chemistry of hydrogen involves 9 species and 38 reactions. You just don't have the reaction H2 plus 1/2 of O2 gives H2O. No, it's all this set of reactions which produces water. So, and this is the simplest chemistry, one of the simplest one. And if you want to handle hydrocarbon flames, it takes a lot more effort. You may have to take into account hundreds of species, thousands of reactions. And of course, you cannot do that by hand. You will, if you do it by hand, you will make mistakes. And of course, the computer allows us to do that. You put the scheme in a software which is called Chemkin, and you are able to handle complex kinetics. Another problem which is of considerable difficulty is that of turbulence, because combustion takes place mainly in turbulent flows. And you know Richard Feynman, who was a professor at Caltech, and I was able to even eat at his table. He was a very famous Nobel Prize winner, and so somebody, I'm sure you've had his books in your hands, his physics books. Well, he was saying that turbulence is the most important unsolved problem of classical physics. Of course, solid mechanics is also not so easy, but turbulence is really a tough problem. And it's not solved. You know, we calculate turbulent flows, but we haven't solved the problem. If we do turbulent combustion, it's even more difficult because there you have the scales of combustion as well as the scales of turbulence. How do we cope with such complexities? Well, you have, of course, the theory. It's essential. You cannot work without theory. It guides you, guides experiments, interpretation, results. You derive models using theory. We have simulation now, and parallel computing is a wonderful new tool. We are able now to solve problems because we have a capacity to resolve very small scales using this parallel computing. But of course, it complicates the task of the person who does the code development. Experiments are very important, and again, you cannot do without experiments in this field. This is why in our lab we have experiments and we have everything else. It's difficult just to say, I'm going to do pure calculations. Those who are doing calculations have to get together with those who do experiments. When you do experiments, you understand the real world. The computational reality comes from the experiments. And now we have diagnostics, lasers, and imaging. We can look at flames with these modern tools. It's again a big change with respect to what was available in the early days. And of course, we have data. We have always been working with data. We didn't wait for the data analyst to analyze data. We have been doing that for years, spectral analysis and coherence, correlations, and so on. That was done well before artificial intelligence. So we use data, of course, that's essential, and we look at data. We do also data-driven or model-driven, data-driven calculations. All right, let me say a few words about computations. For a long time, to do calculations of flows, we have been using averaging. We take the Navier-Stokes equations, and they are what we call Reynolds average. This has given rise to many computational tools that are used in industry. But this is not very easy to do because you need a lot of modeling there. On the other hand, we do direct simulation. That is, we take the equations and all the kinetics, and we place all that in the computer, and we calculate flows. But then you can calculate very small flows, and you learn a lot, but you cannot use that effectively. And in the middle, you have large ID simulation. This is what allows you to get the meteorological predictions. The idea is as follows. You have a spectral, the power spectral density of turbulence here, which is shown. And if you do direct simulation, you have to take into account all the scales, including the very, very small scales. So the resolution has to be extremely, very important. If you do large ID simulation, you consider that the small scales are universal, and you model them, but you calculate the large scales which contain the energy. I'm just showing this plot to tell you large ID simulation in fluid mechanics arrived around 1988. You know, if you do this exercise using the Web of Science, you can watch how a given topic is arising in the scientific community, and you see now it's something that has developed extensively. If you look at combustion, and this is, for example, a typical example of what happens in the Atlantic Ocean due to the flows in this ocean calculated using large ID simulation, something like large ID simulation. You see on one side it's France and Spain, and on this side it's the United States, and you have this flow taking place, and with vortices and in clockwise and counterclockwise directions. The difficulty with flames is that they're very thin, and so you have to find a way to accommodate that on a coarse grid. Even in the LES, which has a very fine grid, you have this difficulty. And this is why in LES in combustion took place later. You see, about 10 years later. It took some time to understand how to handle a flame on coarse grids in an LES framework. And this is also interesting to do. For example, you're working on a topic and you want to know who are the main competitors. It's like it's a competition. It's like when you run and you are in a competition, and you look at you say, for example, I want to see who is working in large eddy simulation and combustion, and this is what comes out, and you see the main lab in this is a French lab, Serfax. The head of the fluid mechanics group there is Thierry Poinceau, one of my former doctoral students. So there is they are first. They're really top level. They've done a remarkable development of LES. The second is DOE, but these are the big American labs in energy. And the third is our lab. So we benefited from what Serfax is doing, and we are in close collaboration with them. Stanford is afterwards, essentially because our postdoctoral students go to Stanford. You know, they love to go to California, and as a consequence, Stanford is there, and Cambridge and so on are back. I'm showing that because people always think, oh, Cambridge is at the top and this is at the top. No, we are at the top here. Yeah. Yeah, they are in the DOE. Yeah, they're very good. You know. This is a typical calculation of a flame with complex chemistry tabulated in this case, and you can see that really it has a realistic appearance. Of course, you have to know that the flames look like that, but yeah, I can tell you it's nice. It really does it, and it does it with a complex chemistry. So you have a complex flow here, which is swirling. In addition, you have these complex kinetics, and you have this very nice result with LES. Let me now go to some experiments and again justify why we do these experiments. In the engine, of course, it's a complicated situation to try to do an experiment in an engine. It would cost a lot of money, and you cannot just put the sensors inside the engine. So you have to do something which looks simpler, and this is our device, which we call MiCA. It's annular, it has multiple swirled injectors, it's premixed in this case, propane and air to begin with, and it's atmospheric. But we now have the capacity to operate also with liquid injection, and we are working with heptane and air, with dodecane and air. This is more complex, and with the sustainable aviation fuels of the future. So this is one area where we have been working, is trying to look at what will be the future fuels for aviation. All this is atmospheric pressure, while in the engine it's at 30 bars. But it's much simpler to do atmospheric pressure measurements. And it's less costly, and you can have students working on that, and you can learn a lot. So you don't need to do immediately the complicated stuff. You have to do the simple stuff first. So let's see, for example, the ignition of this device. You place a spark plug, and at one point, you ignite the spark plug, and how the flame will develop in this combustor. It's like in the engine. You will see that here. I have to use that. Yeah. So the spark has ignited the flame. You have the two branches which move and which finally get together, and little by little everything is established, and you have this combustion established in this annular combustor. And you see, this is fairly recent. We didn't do something like that earlier. And of course, all that takes place in 30, 40, 50 milliseconds. So this is, of course, slow motion. You don't see that. It's there, you know, but this is what happens in a real engine as well. This is called the light round. And you see, it shows this, in case the film would not operate, it shows how this develops. And then I was interested in trying to actually calculate something like that. Is it possible at this stage to do the calculation? And we got ours from Paris. Paris is a European organization to give hours for advanced computing. And we assembled a team to do that with a student who is Maxime Philippe, right here. And here is the calculation. So, whoops. So on one side, you have the calculation. On the other side, you have the experiment. And you see what we see here is emission, light emission from the flame in pseudo colors. And on this side, this is the result of a calculation, LES calculation, with all the models required. And it's fairly realistic. You know, you get the right merging time, you get even the structures. If you look carefully, they are here. You see, these are still images, and you see definitely that you represent this complicated situation. It's ignition, the flows are swirling, you have multiple injectors, it's a turbulent flow, and we are now at this level of being capable of actually working doing this sort of, and then we also did experiments using liquid fuels. So this, in principle, yeah, you can see, for example, that propane air premixed goes faster than heptane air and faster than dodecane air. It's less volatile. This is more volatile, and this is fully premixed. And of course, you can try to calculate such flames as well. So it's a more challenging situation because here you have a liquid phase, so it's a two-phase flow. It's more complicated. You can see that again because it's nice. So the imaging tells us a lot, and we can then try to have this calculated. Let me now go to a topic that I've been working on for a lot of time. In fact, one of my early encounters of a scientist is Luigi Crocco. Do you know Luigi Crocco? He was a very famous professor from Italian origin. And Crocco, yeah, the Crocco theorem. But there is a father, but there is the son. You know, the General Crocco and the son was Luigi Crocco. Luigi Crocco, at the end of his life, lived in Paris, and he knew me. Yeah, and so we had discussions. He gave me his books. He left word that his books would be given to me. And he worked extensively on combustion instabilities for liquid rocket engines. So this work was initiated during the early years of launchers development. So the problem is as follows. You have a flow, you have combustion in that flow, and due to acoustic feedback, you can have a loop, and this can resonate, and then you have a problem, because this will destroy an engine. It can be very harmful to you. It vibrates, makes a lot of noise. This is pure tone. And so we have to study that. And it looks simple, but combustion is complicated. The acoustics and how the combustion and acoustic interacts is not easy. And then this, of course, disturbs the flow, and this loop is interesting to look at. Let me show this film where you can see an instability developing as we, yeah. You see on this side, we increase progressively the equivalence ratio. We make the flame richer. You see it's not very stable here, and suddenly it becomes like that, and there is sound, you know. At that point, I cannot make it loud here, but you hear a definite resonance here. So this is a typical instability. Of course, if you want to work on these instabilities, you need to look at the modes which come into this system. And what is interesting in annular combustors is that you have waves which can go one direction or the other, clockwise, counterclockwise. So you have a degenerate mode. And what happens is that you don't know which one will come in. Will it be a standing mode? Will it be a spinning mode? Will it be a mixed mode? This is an interesting problem. And in fact, we use, to look at the details, the Poincaré block sphere to plot actually this sort of behavior. Well, so it's interesting to, of course, you know the frequency at which this will happen. We have defined the spin ratio actually to say, are we standing, are we spinning? And let me show an example. And this is an example. Our combustor, this is the annular combustor that I've shown for ignition. Now we look at instabilities. And the mode is a transverse mode. It's an azimuthal mode. And here what you see is that this is a mode which is standing. And the microphones which are set on this on the backplane here show definitely something standing. You can see, if you look at these signals, definitely this is a standing configuration. And if you look at the heat release, you see that at one point in the cycle, you have positive here, negative there. Positive is red, negative is blue. And on the other side of the cycle, you have the other situation. And you can watch that here. You see the red here, and then it becomes blue, and then it becomes red. And it's this sort of standing mode. And then you have, at other points during the cycle, you have a spinning mode. In this case, you see the microphones show a wave-like motion. All the microphones are aligned in this way, and definitely you see that there is a wave rotating in this system at the speed of sound. It's a wave which moves at the speed of sound. And later on, what we found is that, in fact, when the amplitude becomes very strong, you can actually extinguish flames. You can hear that, you know, at some points. Now we have the instability at this frequency. Yeah, and these are instances where the flames are extinguished. We will see that in slow motion, I think. No, maybe not. And yeah, this is how it looks. So you start with the flames which are ignited. You see that there is some kind of standing mode here. And after a while, you get a situation where some flames are completely extinguished. And of course, you don't want that. If it happens in your engine, that's bad for your flight. So you hope it doesn't. So you hope the engineering is such that this will not happen. And more recently, what we've done we are actively working on these various things. Of course, one of the goals is to predict such instabilities. How do you predict? And one of the ways to do that is to reduce the model, and we use a reduced order model, and we use what is called a describing function. Let me explain that a little bit. So the idea is as follows. On one side, we have this combustor, which is annular. But here, you cannot do detailed experiments. On the other side, we have a combustor which has a single flame. And here, we can actually work out the transfer functions of the flame. And we establish a dialogue between this single injector and the multiple injector. What you see around the injector is a number of photomultipliers as well. And what we do on the single injector is to develop a database of describing functions. Describing functions are transfer functions, but weakly nonlinear. They depend on the amplitude of the input. So it's better than just a transfer function. It's not linear. It's, you catch a little bit of the nonlinearity of flames. And I just set equations just to tell you that we also work on equations. I was surprised by the complexities that I've seen here. We do some very difficult things. For example, the source of acoustic energy here, which we call the Rayleigh source term, is the combination of the pressure fluctuation and the heat release fluctuation. It's the product which produces the instability. We have also damping. So anyway, and we can, of course, the goal is to get the growth rate. If the growth rate is positive and exceeds the damping rate, then the instability will be there. The whole problem is to calculate this growth rate. And are we able to do that? And this is what we call a describing function, a flame describing function. You see, it's the heat release rate divided by the velocity fluctuation. So it's a transfer function, but it depends on the amplitude of the input. So that's this concept of describing function. And we verified, this is our experiment, rather recent ones, in the Journal of Sound and Vibration. We verified that the flame under instability and the flame modulated externally at the same level of oscillation have the same look. You see the A and B, on one side, one is a self-sustained oscillation, the other one is a forced situation, and they look alike, and if the forcing is not at the right level, it's different. I see that the time is passing, but yeah. One very important aspect of these combustors is the injector. The injector sets the impedance to the waves, and as a consequence, it gives the relation between the pressure and the velocity. And then the velocity acts on the heat release rate. So you have to take into account the injector. You have to measure what this injector is doing. And also the injector is doing some damping. So you have to account for that damping. And when you do all that, when you get your describing function methodology, you put everything together, it is possible to do predictions. And what we show here, you have one injector, the 707, which is essentially stable. You cannot get an instability in the multiple injector combustor. It doesn't do an instability. And in fact, when you calculate the growth rates, they are small, 60 seconds -1, well below the damping rate. And so as a consequence, you can say here, we don't have any instability. The 727, it's a different injector. We looked at families of injectors. And in this case, you have a situation where instability occurs. And you predict that this can happen because the growth rates are now reasonably high, higher than the damping rate. And this is quite exciting because you can replot that. So this is the database, 30 points. You have to do all the describing function measurements. And once you do that, you can do predictions. And these are the values of the growth rates. And you can compare with what you see in the multiple injector combustor. And you find that for 727, which has instability, it looks like it's of the same order. It has the same layout. So we are very happy with that. It doesn't look the same because on one side we plot the amplitude at limit cycle. On the other side we look at growth rates. So that's not the same thing we plot, but it retrieves the essence of what we've seen here. And some very nice experiments we've done is to use combinations of injectors. You take the 727, which is unstable, the blue ones, and the red ones are the stable ones, and you place them. And for example, on this side, if you place them diametrically opposed, you have something which is you break the symmetry, and this is a pure standing mode that comes around. You see the signals at the various microphones, and this is a standing mode. If you put all these injectors on one side, you still have a standing mode, but the level is lower, and we explain that. So this is a paper which has been submitted to the Journal Fluid Mechanics. So we are in the process of responding to 7 pages of remarks, but I hope this paper will finally get its way in the JFM. All right, I was going to tell you a bit about space propulsion, perhaps 2 or 3 minutes. We worked extensively on this topic because it is really even more challenging. Of course, you need the technical performance, but you need to understand how it works. And I told you it's something where you have a very large heat release. The power per unit volume is enormous. We are at a very high level of pressure. You have a multitude of injectors in this combustor. The backplane is full of injectors. The velocity of hydrogen is injected at 200 meters per second, but the flame is stable there. How is the flame stabilized? This was not known by engineers until very, very late. We did experiments which demonstrated. Yeah, and when I take a shower, I always think about rocket engines. You know, because it's a shower head. It looks like that. And so we are above the critical point here. So that's tough. And when you are critical like that, you see under critical, you see droplets, you see the jet is broken, the liquid jet is broken into small droplets. When you're above critical, it's mixing. There is no more interface between the liquid and the gas. The oxygen is at 1,000 kilograms per cubic meter, but there is no interface. It mixes. And this is the structure, and you see that the flame is stabilized on the injector itself. It's able, despite the very high velocity of hydrogen and oxygen, these are reacting very strongly. Well, the flame is located very close to the lip of the injector. This is experiments with methane. Let me just do that. There's a film first here. So this is just the beginning. It's ignition. Then we go to high pressure. The flame is stabilized. This is how it looks. This is a still photograph. And of course, you want now to calculate something like that. So you have a complex equation of state and all these difficulties. And let me do this film. Whoop. And you see this looks realistic. So we have now very nice calculations of such flames. They are complex, transcritical, turbulent, reacting. It's difficult. It's really a complexity of physics, and we do a fairly good job in representing that. Not only a single flame, but multiple flames as well. Now let me jump to the conclusion. Whoops. So what I tried to do, I had many more slides, but I knew that I would not be able to show them. So this is it. Advances have been made, considerable insights. When I compare what I knew at the beginning and what I know now, it's enormous. There is a revolution. You know, we always look for revolutions. People in physics say it's a quantum revolution, but we have done many revolutions here in what we are doing here. For example, this LES is wonderful. It's a real revolution, and not only for science, but also for engineering, because these sort of tools are used by industry. And we still have to work on very hard, because we have the decarbonization taking place. We want to investigate sustainable aviation fuels, maybe hydrogen, and we have a project on hydrogen. So a lot has to be done. And just to finish, this is the group at present time, but I had a number of students before. Véronica Latour, Daniel Duros, he's also retired, but we work together. And Priti Sundararajan, she is now in Cambridge. Nicolas Vess is in our lab, he's working on hydrogen, and Antoine Renaud, Ronan Viclin, and myself. And this I'm saying because a lot of people give you answers that you cannot question, but we want questions that cannot be answered. And Feynman was saying that. Thank you. Thanks.